Okay, this is another video in my series of videos. This one we're going to talk about metal. And we're going to talk about conductivity, and we're going to talk about electrical current conductivity. First, let's reestablish the difference between alternating current and direct current. So this is just a reminder. Everything we're going to be talking about now is direct current, and AC is alternating current. AC is alternating current. Cool. Uh, Alternating current, if you remember from one of the earlier videos, is really a man-made phenomenon by spinning a turbine with magnets in it, north, south, north, south, north, south. Right, you've got this turbine, you're spinning it, and there's coils. There's three at least, one for each phase, but there's probably 9 or some factor of 3. Alternating current is man-made. Especially at the way we use it, it's man-made 60 hertz, which means it's spinning at a specific frequency. And this is alternating current is important, and we'll talk about it in a later video. But in this case, we're going to talk about direct current, and we're going to talk about the role of metals. All right, so let's talk about metals for a second. So we're going to talk about metals here. Metals. So there's this thing called the electron soup model, which is a model for how a metal, so you have a piece of metal here, say it's a piece of steel, piece of iron, Fe, and the way that the way that metal exists, it's just kind of crazy to think about, is inside of here you have a bunch of Fe ions, Fe, Fe, a bunch of Fe atoms, right? And they compose a structure, right? When you smelt something, you're smelting iron, and you're sort of structuring it. You're forcing a structure to the ion. But what's really crazy is what's unique to metals and not to other things is that these iron atoms are sharing electrons. And the electrons might not even be, my understanding is that it's not even like they're sharing one. There might be thousands of them sharing a single electron. And the electrons actually are all moving around too. And this is why they call it sort of the electron soup, is they're just kind of moving. If you just are holding a piece of iron, they're just bouncing sort of all around at random, and they're all being shared. And so there's some randomness to it. But this is essentially, so if you have this piece of metal here, it's just composed of all these iron atoms, and they're all sharing these electrons. And there's other things that can do this, right? So this is iron, and this is sort of a property of conductivity. Iron has this sort of electron soup model. Other things do too. Silver, Ag. Nope, silver's not Ag. What is silver? I can never remember. Iron, silver. What else is conductive? Copper, right? So they all have this exact same model. It's a metal, and there's electrons being shared between all of the atoms. And so what makes this really interesting and what makes this conductive, the whole idea of conductivity is if you have this surface, if you have this metal with just these electrons kind of moving around randomly in there, right? They're just kind of moving around, they're being shared, but they're just sort of moving randomly, and it's relatively stable, but they are moving. The idea of something being conductive is the property of force movement on the electrons. So the whole idea of a voltage and the whole idea of conductivity is you say, okay, atoms, or okay, electrons, don't move that way, move this way. Hey, you, don't move that way, move this way. Hey, you, don't move that way, move this way, move this way. And so you're taking all of these electrons and you're forcing them to move in a certain direction. And one way to do that is sort of to apply a voltage, which just sort of says applying a voltage is you saying, hey, here come a bunch of electrons. I'm going to force my electrons in this way, and the rest of you have to keep moving along with that. And so this is fundamentally what direct current is. Direct current is the idea of taking all of these electrons in this sort of electron soup of a piece of metal and pushing them and forcing them all to go in a single direction. And so why this is important to us is when we talk about what cathodic protection is. Cathodic protection. Cathodic protection and corrosion, right? So let's talk about what corrosion is then. So if you have a piece of metal, right? So we've got our piece of metal here. We're going to talk about corrosion. We've got our piece of metal here, right? And suppose some part of it was exposed to the environment. So say like this little corner over here was exposed to the environment, and the rest maybe is coated or something. But this is exposed to the environment, and we have the four parts that make up corrosion. We have an anode, a cathode. We'll talk about those in a second. We have a metal, and we have an electrolyte. Electrolyte. And so when I say the electrolyte, I essentially mean like the environment here. So there's wetness, there's water, and there might even be some H plus ions. And the presence of H plus ions, the number, essentially the way people measure H plus ions is a thing you may be familiar with called pH. So note that here's what's interesting is you've got in the electrolyte or in the environment out here, you've got these H plus ions. But what we just talked about is in the electron soup. Remember the electron soup? We've got all these guys, right? We've got these little electrons that are just freely floating around. But if you remember from basic sort of electrochemistry, positives and negatives attract. So these H ions, this is why pH is corrosive, is because these H ions are saying electrons, come here, come here. They're attracted. These electrons are being pulled out. And as the electrons are being pulled out, that actually creates a current. So this is like, all of a sudden the other electrons are now, if there's no cathodic protection, all the other electrons are now saying, oh guys, we're going this way, we're going this way, we're going this way. Oops, E minus. And all the electrons are sort of being pulled out this way. And sometimes that might be okay. For instance, if this hole was only a single atom, that might be okay because we wouldn't have it actually wouldn't flow because we wouldn't have an anode. So this is the cathode here. But here's what causes corrosion. So suppose you have another spot open to the environment over here. What's going to happen is all of this current is going to flow this way, and you have some iron element here that needs an electron to stay in place, right? It's sharing an electron with a bunch of other. It's sharing an electron with a bunch of other iron atoms, but all of a sudden, it doesn't have one anymore, right? It doesn't have one because that electron is sort of being pulled through this flow, and this flow is called voltage. It's being pulled out, and all of a sudden, it doesn't have this electron, so the metal just goes like, "Hey, see ya," and it just spits it out. It says, "Hey, see you later. Get out of here." And it spits it out, and so you get an iron. And this is what causes the metal to start to degrade, right? The literally atoms of iron are being spit off here at the anode. This is the anode here, and this also has to be exposed to the environment too. So we'll say this whole section up here is exposed to the environment. And so this is the anode here. So you've got, and these don't need to be far apart. They can literally be next to each other in next like grains of. In the grains of the steel, they can be directly like within like nanometers from each other. But this is functionally what's happening is, and all of a sudden, all these iron atoms are being released, and they combine with other stuff to make iron oxide. I think it's like FeO2. They merge with other stuff in the environment like water, and they become this, and this is rust. But functionally, you're losing atoms. Atoms are these, and this is what happens when there's a coating failure. They call it a coating holiday. This is what's going on. You need two coating holidays, but they could be as small as sort of the grain of the steel. So I guess in the next one, I'll talk about what cathodic protection is because I'm kind of running out of time on this video. I don't like them to be more than 10 minutes. But next time, and so this is this voltage we're seeing here is direct current. This is DC, direct current. So there is a voltage. It's not being applied. It's happening just in nature, right? Direct current. Humans are not creating this. It's just happening in nature. You know what happens if a piece of iron rock is exposed to the earth? Like this is happening, and this is a natural process. Direct current. Cool. So we'll talk more about this next time.